And now for the first presentation for SEE-08, I will invite Mr. Cornelius Satria Yudha from 11 Maret University. He will present his research with the title of The Synthesis of Zinc Oxide ZNO, the synthesis of zinc oxide from zinc-based fertilizer as a potential and low-cost anode material for lithium-ion batteries. So for Mr. Cornelius, please. Are you ready, Mr.
Yes.
Cornelius? Yeah.
Yes. Good afternoon, everyone. First of all, I would like to say thank you to the committee for giving me a chance to present in ICONETSI 2020. My name is Anjas Hutama, and I represent my team to producing oxide from zinc-based fertilizer as potential and low-cost anode material for lithium-ion batteries. To mitigate the current and future energy crisis, many researchers have redirected their focus on green and renewable energy come from sunlight. Harvesting electrical energy directly from the sunlight has become one of the main interests in developing sustainable energy industry. Among various attempts on solar energy utilization, solar cells are considered highly promising to be adapted for large-scale power plant. Solar cells have been commercialized widely, which help reduce the overall fossil-based energy of main country, thus contributing towards greenhouse gas emission level decrease. The battery is a device that can convert the chemical energy it stores into electrical energy that can be used by the device electronic. In everyday life, there are two types of batteries, namely batteries primary that can only be used once, and secondary batteries can be rechargeable. Lithium-ion battery consists of a cathode, anode, separator, and electrolyte solution. Zinc oxide, or ZNO, has been utilized for various applications related to current energy solar cell and as anode material in lithium-ion batteries, which is environmentally friendly and low production costs.
Sorry, Mr. Anjas, we cannot hear your voice. Are you there? I think it's disconnected. Because there is a problem in the connection, we will show the video of the first presenter for the session. Can you unmute the audio?
Test. Hello.
Hello.
I'm sorry. My connection is unstable.
Can you continue the presentation?
Yes, I will repeat my presentation. Zinc oxide or ZNO has been utilized for various applications related to current energy harvesting technology. For instance, ZNO has been used as photoanode in solar cell as anode material in lithium-ion batteries, which is environmentally friendly and low production cost. In this study, zinc oxide powder was synthesized via precipitation of zinc sulfate fertilizer using sodium hydroxide, oxalic acid, and ammonium bicarbonate, followed by high temperature calcination to obtain final ZNO product. The use of ZN-based fertilizer can greatly reduce the overall production cost of material, which is an important aspect and consideration for large-scale manufacturing purpose. Synthesizing ZNO powder precipitation. In the study, zinc oxide powder was synthesized via precipitation of zinc sulfate fertilizer using sodium hydroxide, oxalic acid, and ammonium.
It's disconnected. So Anjas, please unmute your audio. We cannot hear your voice. Hello.
I'm sorry.
Yeah.
And then the ZNO sample were characterized using SRD and mixed with artificial graphite to obtain ZNO graphite composite anode via solid state grinding. Result and discussion. These figures show the SRD spectra of ZNO precursor obtained from various precipitant. Figure A display the ZNO precursor via hydroxide precipitation route. Figure B show the ZNO precursor obtained via oxalate precipitation, and figure C present the XRD spectra of ZNO precursor from carbonate precipitation. All of the diffraction peaks are in agreement with zinc carbonate diffraction pattern with triagonal structure, which correspond to PDF part number 83, 1765. The spectra of sintering of various precursor can be seen in this figure. High intensity and sharp peaks and smooth baseline indicate that the powder has high crystallinity. The crystallinity size of ZNO precursor and ZNO powder sample are listed in table number 1. The crystalline size are calculated using the Based-Fertilizer method. From table number 1, the largest crystallite size of precursor and final product was achieved by ZO and ZNOB respectively. And then 10% ZNO graphite blending and composite sample XRT spectra are displayed in this figure. The diffraction patterns show the presence of graphite paste and zinc oxide paste in every sample. There is no significant difference between blended sample and heated or composite sample. And then electrochemical performance of ZNO graphite composite from various ZNO precursor was analyzed by measuring the charge and discharge capacity of LFP ZNO graphite cell, where the ZNO graphite sample were applied as the anode material. This figure displays the charge and discharge curve. The specific capacity and measure based on LFP weight basis. Based on the figure, the highest initial specific discharge capacity of 88 mAh per grams was obtained by cell with ZNOB graphite anode, which is higher than the capacity of cell with pure graphite as anode. However, ZNO-A and ZNO-C have lower capacity compared to pure graphite. The reason behind this phenomena is still unsure. However, based on XRT analysis, it appears that the precursor characteristic affect the final capacity.
Sorry, Mr.
And then
Anjas,
conclusion.
you have 1 minute.
High purity. Yes, thank you. High purity zinc hydroxide, zinc oxalate, and zinc carbonate is successfully obtained from precipitation of zinc-based fertilizer. The zinc-based precipitate can be easily converted to ZNO via high temperature, sintering at 500 degrees Celsius. All of the ZNO sample have good crystalline properties and Wurtzite structure. Based on the charge and discharge analysis, the highest specific cell capacity was obtained by ZNO from zinc oxalate precipitation, which also has higher cell capacity compared to cell with pure graphite as anode. Morphological and surface chemistry compared to cell with pure graphite as anode. Morphological and surface chemistry analysis of ZNO graphite anode material from various precursors are important steps to be conducted in the future. In conclusion, zinc-based fertilizer derive ZNO as a promising anode material for lithium-ion batteries. This is the end of my presentation. Thank you and good afternoon.
Okay, thank you, Mr. Anjas, for the next presentation. That it is about the developing of the low-cost material for anode lithium-based battery. So I will read the question from the chat box. The first question is from Mr. Heri Susanto. The question is, what is the yield of the zinc oxide and is it economically beneficial? Can you hear my voice? Is it clear?
Yes, I will answer the question. Thank you for the question. Yes, it's economically beneficial. The yield is about 85%. is economically beneficial.
Is there any question from the participant? We still have 3 minutes before we start the next presentation. Okay, Mr. Anjas, can you, this is the question from me. Can you show the slide about the synthesis of the material? I see that you need potassium hydroxide and sulfuric acid. I forgot about the slideshow, but I think it's in the beginning part.
I'm sorry. Can you repeat this question? I can hear.
Okay, I think we have another question from this Epital Goal. The question is, do you already study also about the commercial value using zinc-based fertilizer? You can see the question in the chat if you cannot.
Oh yes. Thank you for the question. Thank you for the question. Not yet. I not yet studying. I'll study also about the commercial value. I'm not yet study. In the future, we will focus on the evaluation of commercial value.
Okay, thank you, Mr. Anjas. I think the time is up, and this is the session for the question and answer. So thank you for your presentation and also your explanation for the question.